All right. Well, I figured it might take them a minute to get the file. We had a little bit of issue with adapters for ye old laptop and iPad stuff going on. So, but I don't want to wait any longer because you guys are sitting around and it's boring just to sit around, right? So instead of just sitting around, we can talk about something interesting. So is anybody here actually familiar with RISC-V? Thank you. I get a little clicker. The problem with just handing somebody a clicker is that you're presuming they know how it works, right? And since I never use these, it's probably going to go backwards, that kind of thing. All right, well, I guess we're live anyway, so I guess I can actually talk about what I came to talk about, which is cool. So raise your hand in the audience if you actually know what RISC-V is or you are experienced with it in any way. Anybody? Man in the back. Another man in the back. Anybody in the middle? Somebody up front. All right, great. Well, I'm going to show you how to hack an architecture that nobody apparently understands or knows, which is great. This is a good thing because now you'll all know how to hack something that's going to be really big in the near future, which is always fun, right? So the first thing we're going to do, see, I don't know how to use the clicker. I'm hitting next. Is that not a thing? Does that not work? Yeah, you can just do that for me if you want. Is it not syncing? Oh, okay. All right. Yeah, cool. So as you can see, typical demo time failure is about to happen. So let's see if that happens. In the last couple of months, really about last 6 months, I've gotten really deep into this new architecture called RISC-V. And my interest there is developing new technology that can be used in the future of IoT. Really mobile and IoT. People are using RISC-V for everything. Google internally is apparently either currently working on or about to work on some of their TensorFlow processors by architecting a new RISC-V chip to manage that stuff, which is really cool, right? So internally, Google's TPUs are apparently currently some kind of a CISC architecture, but they're custom designed by Google. RISC-V, being an open architecture, allows them to use something that's standardized, something that's more open, that they can build an ecosystem around, especially internally, without having to manage all of the internal cruft required of developing your own silicon, which is a huge pain in the ass, right? Like, nobody wants to spend a huge amount of time developing for something that only a few people are going to use internally. So switching to RISC-V might be a really big deal, especially because RISC-V has a lot more longevity than other processing architectures. One thing, it already has a definition for 128-bit computing, which is awesome, right? People have been talking about 128-bit computing for quite some time, more theorizing what it's going to be like. Well, RISC-V already has a definition of what that needs to look like. The instruction set architecture actually specifies what those instructions should look like and how they should be defined within memory. So we have a really great way of already having the next generation of computing architectures in this new definition of a processor. So here, we're going to show a little video of me hacking the current implementation of RISC-V, which basically proves that the security architecture is still a little flawed, right? So I'll give you this, yeah, go ahead with the video. I'll give you a play-by-play after, but this is initially just the proof of concept. So you can see I'm loading up a virtual machine here. Oh, brilliant. Cool, thank you. So here, we've got the virtual machine loaded up in QEMU. I'm logging in. I'm executing my little application from userland. So you can see here all these bytes are being dumped out of memory, and they match those instructions up there that I'm highlighting. Then I execute another application that overwrites the machine code, and now you can see when I read back memory, all of those bytes have been altered. And then I execute the exploit, which actually breaks out of the privilege mode that Linux kernel is currently executing in, and it's essentially the equivalent of breaking into trust zone. So if you're familiar with the ARM architecture, you'll know that basically the way that it works is you've got your standard operating system running in normal memory, and then you've got essentially a machine layer set of executable code that's running at a higher privilege layer that the supervisor or operating system cannot touch. Right? So the Linux kernel should never ever be able to alter memory within something like a trust zone secure memory area, right? But this is the equivalent of doing that, okay? So very quickly on me, my name's Don Bailey. That's me and my cute little boy Pierce, who happens to be in the back there. I am a security analyst. I've been doing this for about 17, 18 years. I was the first guy to hack a car back in like 2011 at Black Hat. I've been doing hardware architecture security for quite some time. I wrote the GSMA IoT security guidelines, if anybody's using that for defining hardware security. That was written by myself along with everybody in the GSMA. We wrote that as a team. It's an excellent guide. If you're interested in IoT security, you should definitely check that out. More importantly, what I do is design secure, resilient systems for mobile and IoT. And I mentioned that earlier. That's the reason why I'm interested in RISC-V. So I spend a lot of time and energy researching the entire processing architecture, combing through every single aspect of the processor definition, the privilege model, the instruction set architecture, et cetera, to find vulnerabilities. Well, what you just demoed, or what I just demoed for you, is the first and really only known exploit for the RISC-V architecture currently. So for those wondering, there is actually a chip in production. So Sci-Fi, the company, does produce in silicon a chip that you can buy, and that's available on the Sci-Fi's, the Freedom FE300U or something like that. But basically, if you go to the Sci-Fi website, you can download all of the open source information about their board, and you can order that demo board of an actual silicon RISC-V chip for $50. So it's pretty cost effective, right? Very cool architecture. First silicon chip made by Sci-Fi. I've got one. It's a great demo architecture, great to play with. They even kind of built it similar to Arduino. So you can kind of plug and play. You don't have to read all of the manuals to get code working. It's quite simple. So in order to understand that attack that you just saw in video, you have to understand the privilege model. And I mentioned a little bit about this, right? It's very similar, kind of. Think about it. I would like to think about it from the terms of trust zone, right? So technically in trust zone, you have a separate area of memory that's quote unquote secure, and code executes there. In RISC-V, the current definition has 4 security models, right? So user land is typical. It's what applications run in. That's what everybody's used to. And then supervisor is where the Linux kernel actually runs, or whatever kernel that you're actually executing. And then the next layer is the hypervisor layer, which is now going to be deprecated. They initially just kind of said, this is what we think is going to go here. But then they decided, you know what, it's silly just to have this. We should actually just implement hypervisor technology in the machine layer. So that, in newer versions of the RISC-V specification, that's going to be deprecated. It's going to be cut out. So what's cool is the machine layer. So the machine layer controls the entire environment, right? And the entire environment being not only physical memory, but all peripherals in the system that you want a supervisor to see. And this is where things get cool, right? Because you already have the machine layer of instructions executing at the highest privilege. The Linux kernel operating system can't touch it. User land can't touch it. This is where hypervisors really should live, so that you can have multiple supervisors running in different areas of physical memory that don't impact each other at all, right? So there's really no reason to have a hypervisor layer. You can just have the machine layer, highest level of privilege, basically doling out different privileges and peripherals to whatever operating system kernel is running, right? So the goal for an attacker is obviously to circumvent this layer model. So this gets really simple, right? Getting from user land to the kernel is a total kernel implementation thing, right? We worry about that at the Linux kernel layer, FreeBSD kernel layer, whatever you're implementing. We don't really care about that here because we're attacking software at that point, or at least the logic of the software running on a particular architecture. So not my interest. I'm excluding that from the security model for simplicity purposes. The more important thing is to elevate privileges from supervisor to hypervisor or to machine, because obviously then you have reign over the entire system. So in this particular exploit, the privilege architecture of RISC-V made a really critical error. So it was defined correctly initially in that if you're running as the Linux kernel in a supervisor layer, you should not be able to access any of the registers that are defined for the machine layer, right? Those are supposed to be separate. You have supervisor layer registers, and then you have machine layer registers, and they point to different things. They control different things. So the supervisor layer should never be able to touch those registers, period. Okay. So what's really cool about this exploit and about the privilege definition from an attacker's point of view is that they missed one really critical area of security, and that's the virtual memory scheme. So as everybody in this room probably knows, when you have an operating system, the operating system is required to alter all of the page tables, the page table directory, all of these things, to control virtual memory for all applications running in the system, as well as the kernel that's executing. If the kernel needs more memory, you have to alter the page tables in order to add new physical regions onto the page table directory. So now you can map, the upper part of memory into these new page tables and give access to, extended heap or something of that nature, right? So every time a new userland application runs, you have to, again, alter the page tables to dole out permissions for those pages, access to userland applications for those pages. So, the TLB and the CPU actually understand how to translate virtual memory to physical memory, right? Well, the problem with that is if at the machine layer you define what the base address of the page table is going to be in physical memory, but then you give the supervisor layer the privilege to alter the page tables in memory, all I do as an attacker is what? Somebody out there is thinking it, I'm sure. But you essentially create a new mapping to the physical region of memory that the machine executive code exists, create a virtual mapping for it in page tables, and then start accessing the virtual code, right? So what my exploit does is it basically says, okay, what's the base physical address of DRAM on the computer that I'm running code on? Because that base physical address is where the first executable piece of code will run on reset. So when the computer resets or the CPU resets, it says, okay, what's the base address for code? That's probably DRAM. What's the base address in physical memory for DRAM? 80000000, right? So it loads code there from some storage application, and then it automatically traps and returns to that address. Well, now I know implicitly where that machine code lies in memory, right? So all I have to do is set up that virtual mapping for that physical address, because I can't touch that physical address myself. So I just create the virtual mapping, and now I can access that virtual page, or that physical page, and I just alter the code there. So now I have governance over every single piece of code executed in the machine layer. I may not be able to touch those registers directly, but I can alter every bit of code that's executed at the machine privilege layer. And that essentially allows me to break out of the supervisor layer and into the machine layer. So that one simple little bit of logic, which is initially kind of difficult to see, right, when you're implementing a system like this, because you know logically the supervisor layer requires governance over the page tables, but the machine layer requires physical security in order for it to be safe, in order for it to be protected against higher layers in memory. Well, that contention is difficult to deal with, right? So now we've proven that exploitation of that works in order to get code execution. So basically what I did, and this is how you make it clean, because this is otherwise kind of a screwy exploit. It sounds simple, but when you actually implement it in practice, it's kind of a pain in the butt, right? Because you can't just access the machine executable code region and start overwriting whatever. Because most of that code is not going to get called from supervisor land. It's never going to run. Or you're going to try to, you're going to cause a reset, cause a panic. The CPU is going to reset back to the initial address, but it's probably going to reload everything from storage and then start executing that code again, right? Which you don't want. That's pointless. Then you've basically just wasted the entire exploit. So the clever thing to do, or I guess the sensible thing to do, not really clever, is to find the trap address in the machine layer that says, okay, when the supervisor needs the machine layer to do something, it's going to execute a supervisor call. Or in this case, RISC-V language, an E call, right? That's the address that you want to overwrite. But you can't overwrite just the base address of the trap because there's actual real work that needs to be done at that layer. So instead, what I did, I found a stupid function that actually just didn't need to be triggered at all, which is the shutdown call. So in no instance am I going to want to shut the system down while I'm trying to exploit it, right? Never going to happen. It's not useful to me. So I basically just overwrote the opcodes that perform the system shutdown, and then I perform the call to the machine layer to say, I want to shut the system down, but actually it's executing my instructions, right? So again, the process is virtual map that physical address of the mcall trap into my accessible memory at supervisor layer, alter each instruction to do something useful, and then basically flush the TLB to ensure that the instructions are now in system core, and then cause that machine trap to occur so that I can get my executable code to run. Boom, done. So in this proof of concept, I didn't bother actually writing some cool exploit because why? It's a proof of concept. The only thing that really is necessary is that I show that executable code can be triggered. So in the video, all I'm doing is just executing illegal opcodes to show that the trap is actually occurring, and I can get QEMU to basically fault and hang, which is what you saw in the video. So the solution to this, actually, I do all of my research a priori. I don't do things a posteriori because it's not useful. Like if you really want to learn a system, it's useful to do things a priori if you're kind of obsessive. If you want to learn from other people and other people's experience, which is also useful, then you're more looking at a posteriori type of learning. But for me, I've found over the years that if I'm learning a new system, a priori knowledge is better. And what I mean by that is instead of actually learning what people have fixed or are in the process of fixing, analyze everything that you can in a particular system, find out what the current vulnerabilities are by reading all that documentation, and then see what people are implementing as a fix, right? Because then you're caught up to speed with everybody else that has started from day zero. Now you're up to speed with them, and basically, instead of trusting their judgment and going backwards to see if they're right later, that's a huge pain. It's like engineering security later. It doesn't work. So basically, I implemented this exploit before I knew that there was a solution to it proposed by the RISC-V team. So 15 days ago, these guys actually proposed a physical memory protection scheme. It's not implemented yet. It's only a proposal in the new version of the specification. So if you look on GitHub, you can actually see there's a new push order to say, hey, we think this PMP, physical memory protection, is going to be useful. Let's start talking about the specification. That happened 15 days ago. So essentially, their solution, which would have been my solution as well, is you restrict the amount of physical memory that's accessible to the supervisor layer. So now you have the machine layer essentially running in a protected area of memory that's not even visible to supervisor. So a supervisor, when it tries to create new page tables, it can only create new page tables within the area of virtual memory and physical memory that it has access to, nothing else. So it's really that simple. It requires a small silicon change, but the amount of silicon required to implement that is actually quite small. So it's not going to be a huge cost when it comes to actually implementing this in a physical chip, which is great. So if you want to know about RISC-V in general, there are some really cool things that you should know. So the death of ARM is inevitable, and there are some reasons why that's true. Number one is primarily cost. I mean, when we think about the cost of an ARM chip, it's awesome from the implementation of something that I would design, like an IoT thing, right? Because at that point, you're looking at it from the cost perspective of 99 cents per chip. If you're looking at an ARM Cortex M0 Plus, right? And what's great about that from a cost model is that I can go implement the next wearable technology as an M0 Plus without really having to scale much in order to sell my product at a reasonable price. So I can really get away with selling my device at like $5 a pop because I'm using a really cost-effective ARM. The problem is that if you want to build resilient system or trusted systems, you can't use technology that's so cheap. You have to start getting more and more into the more costly chips, right? So if you want something that actually can execute quite well, you have to use a Cortex M4F, because that actually incorporates floating point into the technology. So now you have like a real chip. You don't have to run everything in software, which is stupid, right? If you want to incorporate trust zone into your chip, you're going to have to start paying 4 times as much as what you would for an M4F, but now you have a trust zone involved in your chip, but you've basically edged out any of your competition or allowed them to gain a foothold on your technology if they don't care about security at all. If they don't need trust zone and they don't want to have a Cortex M33 or Cortex M23, then they're basically going to say, well, we're going to go with the Cortex M3 for basically a quarter of the cost or less based on volume, and we're going to beat you every single time. So what are your consumers going to go with? Are they going to go with the technology that costs them maybe twice as much, and the only difference is that it's secure? Consumers don't care, right? They're not interested in that metric. They want to know that their stuff is secure, but they don't want to pay twice as much for it. That's silly. So instead, they're going to go with the cheaper model every time. And that's what we're seeing in Android worldwide, right? That's primarily why iOS only exists in the first world. But the rest of the universe uses Android because it's cheap and it's easy and it's you can pick it up anywhere. You don't have to pay a ton of money. I can get an Android for $10, right? And it's going to be just as good of a smartphone as I need it to be, right? But it's going to be hackable as shit. But the problem is, when you get to an ARM Cortex M23 or M33 level, the amount of money that you're paying per chip for that trust zone is about the same as you would pay for a Cortex A9 or a Cortex A5, albeit probably without trust zone, but still, you might as well step up in capability and get a real processor instead of running a microcontroller, because that's nonsense. Like, why would you pay that much for it? You might as well just step up your capability and run a processor at 1 gigahertz instead of 48 megahertz or 100 megahertz. There's no reason to spend that money. So RISC-V is the first opportunity for implementers that will allow us to completely destroy that model. And that is truly exciting. So if anybody's researched going out and actually implementing their own ARM, like I have, the initial pay-to-play model for ARM is you're going to foot up around $1 million or more in order to just start in with the ARM ecosystem. That's basically trademarks and all that other good stuff that you need in order to go say, I have a piece of ARM technology and I can build ARM technology myself. And then from there, you have to pay for IP. So you pay for somebody's UART peripheral, you're paying for somebody's memory bus, you're paying for all these different things that you're incorporating into the CPU, right? So that's another cost. More importantly, every single time that you sell an individual ARM chip, you have to pay royalties back to ARM, which can be anywhere based on your volume from 1% all the way up to 4%. Now think about that. If you have a $1 chip, you are going to be spending 4 cents of every chip that you manufacture and sell back to ARM. When you're paying for the amount of engineering that it requires to build silicon, especially at scale, that's a significant hit of people's ROI, right? So RISC-V doesn't have any of that contention. You can build a RISC-V at spec in a few months. You can manufacture physical silicon in 6 months. You don't have any pay-to-play upfront, no $1 million deposit, whatever you want to call it, and there's no royalty to pay. So every time I manufacture a chip and sell it, I don't have to give anybody 4%. I don't have to give anybody 0.5%. Nobody gets that money. The only people that I have to pay are the people that I get my intellectual property from. So I buy some kind of a UART from so-and-so person over there. Cool. I'll give him some kind of a licensing deal. Fine. That's acceptable. I'm going to do the same thing with ARM or any other CPU technology. But in RISC-V, that's the only dollar that I'm paying out to somebody else, which is awesome. So now that means that we can build significantly better systems, more secure systems, more resilient systems at a fraction of the cost of what we can do with ARM. And that is completely game-changing. So you want to know why Bunny Huang, one of my personal heroes and one of the best hardware hackers in the world, he is one of the founders of Low RISC, who I'll talk about in a minute. But Low RISC, that organization, is a nonprofit whose only goal is designing secure CPUs, more for mobile and server and desktop and things like that, not really what I'm interested in, but with secure memory. And they want to do it at scale so that they can start selling cell phones, which has been a goal of Bunny's for years, for a fraction of the cost of what they would normally sell, but with capabilities that are equivalent to, say, an Apple iPhone, which is exceptional. That's what we want to see. That's the whole reason for going with RISC-V, is this type of technology, right? And the greatest part about it is I can stand up here and talk about this all day, and I'm not even selling anything because this is entirely open source. Anybody can go out, download this specification, download open FPGA implementations, and go build their own silicon. You don't have to pay to do anything. It's great. So, once you go through the process of developing and architecting your own system, you end up with really elegant solutions for security, right, that are very low cost. And I just mentioned low risk. Well, tagged memory is a big implementation at the low risk team. The low risk team's technology is basically taking a holistic look at how control flow architectures work. So if anybody here, and I'm sure there are quite a few people, how many people write exploits or deal with exploits in any way, vulnerability research? It's okay to raise your hand. So we're friendly for you people here. So in a RISC architecture, a RISC-V architecture, tagged memory is really exceptional for defeating control flow. So if somebody overwrites a return address or a similar type of object, a controlled object, you can actually implement at the hardware layer a piece of metadata that tells the CPU, do not let anybody alter this data from outside of these boundaries. So you can say, these functions or these instructions will allow access to this region of memory. Other pieces of technology cannot touch it, period. So if you're basically trying to store a chunk of 32 bits or 64 bits at a return address's address, it will not let you overwrite it, because the TLB and the MMU itself in silicon will look at the memory data or the metadata and say, oh, this address object in memory is not allowed to be written to by a store. It can only be written to by a call or a branch with return, right? Anything that would legitimately load an address into that region of memory. So when you have these kinds of things, it really significantly limits the amount of work that you have to do from a security perspective to disallow any types of buffer overflow attacks or heap attacks or things of that nature. Basically, any attack that would overwrite a return address in that structure would be disabled. Now, that doesn't really help with things like ROP, but it does help when you start a ROP chain. Like, in order to start a ROP chain, you actually have to overwrite a return address somewhere, right? So starting that chain is a problem, but if you can figure out how to start that chain, then the return address or the return-oriented programming or whatever you want to call it will still essentially work. So there are still more things to be done. The other limitations with something like tagged memory is it requires a massive amount more silicon, right? Because now you have more instructions that you have to support. So you have to support tagging instructions, you have to support removing tags, so that's more instructions required, that's more silicon required. For every single address line that goes into the TLB, it also has to have associated metadata. So now you have to manage the metadata as well as the address lines in every part of the MMU, TLB, et cetera. Right? So now every CPU or object has to be aware of this type of tagging technology, which is why you really rarely see this technology implemented, right? Because the costs skyrocket. And it's not just silicon, it's actually the ecosystem involved in developing technology as well. Because if you have instructions for tagging, that means that your tool chain also has to support it. And if your tool chain supports it, then you have to also catch the faults, right? So if you actually see in an application, oh shoot, something just tried to overwrite a return address, how do we differentiate between code that's written badly and code that's being maliciously instrumented? So the ecosystem has to allow for some kind of a delta between those two attacks. You know, and I'm saying attack here is just a classification of something that's corrupting something. Not necessarily maliciously, but it's still an attack on a stable environment, right? So how do you actually implement that? Well, it requires not only toolchain alterations, but it requires applications that understand how to process the information to determine whether or not these things have changed in a malicious way. And then somebody actually has to listen to the results of that information to know whether or not there's an attack occurring. So basically, you're changing the entire way that admins look at services, right? You're changing the entire way that an operating system, like a mobile operating system like Android, interprets faults. You have to set up, basically, pushes that, you know, like you would see in Android or iOS, some kind of memory dump when an event like this occurs. That data has to be sent back to the back end. Some kind of company has to have somebody reading through that data and actually analyzing whether or not it's an attack, and then talking to Q&A, and then talking to engineering, and then talking to security to determine whether or not there's a problem. This is a very, very long chain of involvement between multiple organizations, multiple people. It's really not ideal, right? So that's the reason why we don't see tagged memory implementations very often. Regardless, it's still a very important technology. And when you have something like RISC-V that's already extremely low cost, you can add on new technologies such as this that basically allow you to spend money where you think it's really important, because you didn't have to spend tons and tons of money already just implementing the processor and building the silicon itself. So you've saved yourself a heck of a lot of a headache. You can add more headache just to support, you know, your need for making yourself sick, basically. Another cool thing about the RISC-V architecture that I'm involved in is the security of debugging. And that, to me, is very important, because the number one way that we see attacks in IoT is really through the debugging system, right? Because usually the goal with technology is very simply and quickly accessing executable code, or basically instrumenting executable code in some way. Well, the easiest way to do that is just bypassing whatever quote-unquote security is implemented for the processing system, or basically system on chip. So everybody's probably familiar with most of these standard attacks, but the standard attacks that you would see in embedded systems and IoT, et cetera, are really simple attacks. Most of the time that you don't really have to do a lot of glitching, you don't have to do SPA, DPA, that kind of stuff to extract whatever code is going to be checked for on boot. Really all you have to do is just guess whatever password's being used. And in most cases, the password is actually stored somewhere in Flash. So you can just extract Flash by attaching a NAND reader or a SPI reader or something in that case, and then finding basically in memory where that should be stored, and then using that password over a serial port. It's really that easy. In most cases, you see system on chips that are being sold en masse, especially Wi-Fi chips for IoT. they have two attack models that are extremely popular in that I get, code execution with nonstop. Most clients that have this model, I end up just recommending that they go with a completely different architecture because this is a waste of their time. But basically it's, oh, there's a password. That password can be easily found through sorting through Flash. Or, oh, the firmware itself inside of the system on chip disables JTAG at a certain point at boot up. So you're basically racing against that firmware to tell it, hey, I'm going to take control over JTAG or SWD or whatever it happens to be. Then you immediately gain access to the system as long as you win that window. You win that race, right? So that's the cool thing about what we're doing in RISC-V is we're eliminating the potential for all of those things to even occur. We can sell system-on-chip capability with debug security by implementing much cooler authentication schemes. I mean, people can still screw it up, right? We can still see system-on-chip vendors having this exact same problem if they implement things differently, but I am the guy currently that's writing the specification on this new debug security architecture for the RISC-V team. So that's my goal, is to implement this correctly. So basically what I'm doing is augmenting the existing definition of the RISC-V debug architecture authentication scheme. Right now, it's basically two registers that you can access before the core is instantiated. So before JTAG is actually turned on, there are two debug registers that you can access, auth0 and auth1. And you're basically just writing 32 bits to each of those registers to say, hey, here's what I want to do. So currently you can implement kind of the same password scheme that you would see in other chips. But in this case, the RISC-V way is that you basically load two integers into those authentication registers. And if they're correct, it'll open up JTAG. The augmentation to that is to actually use those two registers as a very simple serial protocol. So I write into one register and I read from the other register. We basically have a circular buffer that allows me to write data into the core that's passed on to silicon that handles authentication. So we've taken away this simple bit-based password scheme that's very common to embedded systems, and we've created a very resilient and easy to augment security model that uses essentially a serial port based in two accessible registers. All of that data is then passed to IP in silicon that verifies the messages that are passed back and forth over these two registers. So the cool thing is that now we can implement any type of authentication scheme we want. And in the debug specification is basically going to say, here's an example of how we're implementing public key authentication. So now we can do public key authentication where something can be signed. We don't actually have to store a security key in silicon or somewhere in like mask ROM or something of that nature. What's really easy to do is we basically just have a signature checking algorithm that ensures that something has been signed by the proper key. So you basically say, all right, we're going to sign this authentication message. This authentication message is going to validate open access to JTAG, but it's also going to be signed by this root key for this manufacturer. So you get the ability to have this dual signing that can be validated in silicon or mask ROM that no longer has to be bothersome to implement. You don't have to implement that at all if you don't want to, but if you want that functionality, the silicon will be there, the IP will be there for people to be able to validate those authentication tokens securely, and now you can have JTAG running all the time. You can shut the peripheral off to save power, but you never ever have to have that running all the time, and you never have to disable it in order to be secure. So you no longer have this race between when your firmware executes and shutting off JTAG from abusive users. You now have the ability to, at any point in time, validate somebody using public key security that should legitimately have access to that particular set of devices, which is really exciting because that's what we want. As engineers, as security guys, you never want to say, oh yeah, go and disable JTAG. You should never have JTAG accessible in production. That's actually bullshit. You should never tell anybody that. And the reason why is because it's not usable, right? In the real world as an engineer, I want to be able to access JTAG when a system is failing and it gets shipped back to me and I need to figure out why it's failing. That's exactly why JTAG is there. I don't want to disable a feature that's going to allow me to learn more about why my product is a problem, right? So the solution to that is, instead of wasting a bunch of time using simplistic security models for something that's actually extremely important, implement it correctly, but implement it as an option that people can opt into if they feel they're going to be building technology for people that are in those situations where that architecture is required. And for us in IoT, that's definitely a critical piece, right? Especially if you're building IoT technology that affects human life in any way, as in telematic systems, anything to do with pacemakers, blood types of systems, blood sugar, that kind of thing. Those are all critical systems, and those kinds of systems need these kinds of protections. That way you can ensure that somebody hasn't altered the code or some kind of technology from the point that the device has been manufactured to the actual hand that's where the customer is actually using it. So application attacks, I'm really only going to cover this briefly. I was going to cover this more, but it's actually not as fun as I was hoping it was going to be in RISC-V. And the reason why is because it's really easy. There are a couple of points that I do want to make, though, that are really important in RISC-V. RISC-V has similar models of execution to something like ARM. So everybody in here, I'm sure, is familiar with ARM and familiar with Thumb. But are you familiar with how ARM executes Thumb and vice versa? Anybody? Quite a few hands. Does anybody want to shout out the requirement of moving from one instruction set back and forth to the other? Shout it louder. Exactly. So in ARM, you have to jump to a certain type of address, an unaligned address, in order to jump from ARM to Thumb or Thumb back to ARM, right? Which is annoying because then that means you have to have a certain bit pattern in memory in order to execute a certain type of code. But what's really cool in RISC-V, if you have the C extension or the compression extension, you can automatically execute 16-bit code without having those context switch problems. So there's no bit that you have to set. There's no unaligned instruction that you have to hit. You can basically just jump to compressed code and execute it directly without any problem. And that's really cool from an exploit development perspective for two reasons. Number one, the shellcode payload that you then insert into memory can be massively smaller because now you don't have to worry about constantly figuring out a way to trigger your compressed code or Thumb alike for RISC-V, which is cool, right? But even better is that if you're doing something similar to return-oriented programming, now every single 32-bit instruction that's already in memory on RISC-V is also two 16-bit compressed instructions automatically. And you never have to, jump to a certain address or have a certain bit set in your return address or whatever in order to reach that type of code. It's just immediately accessible. So from a ROP perspective, it's actually really fun. But otherwise, it's actually quite easy, but it's really the same as any RISC that you've ever implemented. The compression thing is the really only cool thing that I wanted to talk about, aside from one other thing, which is that, as I mentioned earlier at the beginning of the talk, RISC-V, by definition, includes a 32-bit instruction set architecture, 64-bit, and 128. So if you want to implement executable code for 128-bit architecture, you can do that currently. They don't explicitly define what the 128-bit versions of the instructions are in the document because there's really no reason to. They basically tell you the definitions for the 32-bit. They have the 64-bit extrapolation of what it means to extend to 64 bits, and then you can extrapolate even further to 128-bit to basically define the differential between each architecture. So if you're interested in writing your own 128-bit exploit code, you can download Fabrice Bellard, who's a very well-known, brilliant hacker. He was the original author of QEMU. He wrote a RISC-V emulator called RISC-V EMU that's available on his website, bellard.org. It currently allows or implements a 128-bit instruction architecture. So you can actually today write 128-bit code and see how it works. I wrote the first 128-bit exploit or demo exploit just for the hell of it because I thought it'd be cool to write the first one. I'm not going to demo it now because we don't have time and it's actually not as cool as you would think. But the code is going to be available on GitHub so you can download it from there and play with it yourself. The other thing that I want to mention about the architecture subtleties in RISC-V is that there is an embedded subset. So the embedded subset of RISC-V, or the E extension, basically takes the compression aspects of RISC-V and gets rid of a bunch of unnecessary stuff and reduces the amount of registers from 32-bit to 16. And the reason why I want to mention that is because exploitation in that environment will be slightly different because the calling model from calling a particular function to another function is slightly different if you're writing buffer overflow code. But more importantly, it's really cool from a cost perspective because if you want to further beat ARM in development of something similar to a Cortex M0 Plus or even a Cortex M4F, you can reduce almost half of your silicon cost by implementing the embedded variant of the RISC-V architecture, which is 32-bit only, but at that point, if you're building those kinds of microcontrollers, you really don't care. That's not necessary. So that reduces your costs even further, which is even why, to me, RISC-V is even more exciting. So I just want to give a very brief shout out and thank you to these particular people from the Sci-Fi team and community. Stefan Arir, especially, has been a very interesting character to get to know. He's very brilliant and he's very involved in the RISC-V community. He's another security researcher like myself, but I think he's more of an engineer. He just has a really good knack for security in general. But every single thing that I've tried to implement, he's always had a comment on, and it's always been valid information. So if you're interested in following the RISC-V security, environment or ecosystem as it grows, I'll probably be somebody to follow, but Stefan Arir is definitely somebody to follow as well. Ron Minnick, an old friend of mine from Plan 9, he is currently at Google implementing RISC-V architectures for Google. He is an amazing engineer, and he has been for decades. He has an extremely large amount of experience. He's definitely somebody to watch in the RISC-V space, as well as Megan Walks, who is basically one of the lead engineers at Sci-Fi. She's an exceptional engineer, and she's also the lead of the, well, I think she's the lead of a couple of teams, but she's basically currently the lead of the debugging specifications team. So I'd just like to briefly say thank you to everybody for attending. And this is the URL for all of the information on RISC-V and my security models and hacks. So later today, I'll actually upload all of the exploit code and data for the demo exploit that I showed at the beginning of this talk. All of the code to implement that, all of the logic as to why it works, and the Linux kernel alterations will be available at this website. If you're interested in developing 64-bit payloads, shellcode essentially for RISC-V, there's code also available there. I have existing payload now that you can play with and use, as well as demo exploits. I've talked with the Metasploit team. The Metasploit team is going to take some of those payloads and incorporate them into Metasploit. So in the near future, you'll already have RISC-V shellcode available when more applications are available on RISC-V architectures. So that's going to be the GitHub to watch if you're interested in hacking this architecture. But otherwise, thanks so much for coming. That's all.
Thank you, Don.
Do we have time for questions?
We do.
Great.
Any questions from the floor? Or would you prefer it off stage? Yeah? Oh, well, okay, this one.
is there anything in the RISC-V specification that gives some assurance that the instructions are executed correctly? So if they're fetched, decoded, and executed correctly?
Can you say that again? Some of that was muddled.
So the instructions in RISC-V, when they're fetched, decoded, and executed, is there any assurance that this is done correctly?
Oh, I see what you're saying. So the RISC-V privilege architecture, the only protections that you really get is the definition of each layer of privilege. There is no specification currently that identifies validation at that level. It's definitely something that I can't speak for other organizations, but I know that other organizations are implementing some kind of basically attestation at the instruction level, but I have no idea how far along that is. And it's not in the spec, so I'll say that. So I think in the future, that's definitely something that should be added to the specification, but it's not currently. But there are implementations that are in the works as far as I know. So, yeah, no problem.
Any other questions? No? Okay, well, thank you very much, Don.
All right.
Sorry we didn't have time to do a quick introduction, but as you all know, founder of LabMouse Security, and thank you very much for your RISC-V architecture talk today.
Yeah, cheers. Thanks, everybody.